nervous astronomy students a midterm today, and oh my goodness, it was stressful. But let's get going with physical science. And we have a fairly simple lecture today, but the topics that we're going to talk about, we're going to be talking about until April, until May, until the final exam. Because we're going to be talking about Newton's laws of motion. And so when I tell you that the final is cumulative, it is. But actually the midterms are cumulative as well, because every midterm we're going to be puzzling things out, probably using F equals ma, Newton's second law. Now last time we talked about the first law, which is the law of inertia that was developed by Galileo, and Sir Isaac Newton said, yeah, let's use that as my first law of motion. Galileo was right. This is the one where it says if an object is in motion at a constant velocity, so speed and direction constant, south 2.5 meters per second or whatever it happens to be, and if there are no external forces unbalanced acting on it, it will stay at that velocity until something does act on it externally. All right? Now, that's kind of an idealization. We talked about that. But a very practical example of that is just riding the UCF shuttle bus. And, of course, our textbook mentions that. If you're on the bus and the bus moves forward and you're not really hanging on to anything, the bus is going to go one way forward and you're going to tend to tip over backwards. All right? And so you definitely want to hold on. And similarly, if the bus turns to the right, you're going to tend to get bumped over to the left, because you're going to, the bus is going to the right and you're going to keep going straight ahead, constant velocity, because you're not bolted down to the bus. The bus is getting forces applied to it by the steering wheel and tires and stuff. But you're not, except for your feet. So if you keep your feet on the bus, you have a chance. So this idea is that you stabilize yourself left and right, fore and aft, unless your bus never changes its state of motion. But anybody that knows or has ever ridden on the UCF shuttle bus system, you know that those guys, I'm not going to call them maniacs, but I am going to say they drive. It's not exactly smooth taking a ride with those guys, but that's as it may be. So that's an example. That's an everyday example of Newton's first law, Galileo's law of inertia. And Galileo developed that law of inertia based on his thinking about motion, especially motion on inclined planes. He had studied motion on inclined planes, and he knew that depending on the tilt angle, marked theta in this diagram, Greek letter theta, he knew that the more tilt angle, the more acceleration you're going to get down the ramp. And if you diminish theta, less steep, shallower and shallower angle, he knew that, well, you're still going to have some force down the ramp, but it might not be a whole lot. And he worked it out geometrically. So, for instance, if this big white vector here going straight downward, if that's the weight force on this pentagonal shape here, then of that weight force, some of it is going to produce a force down the ramp. All right, so try to sketch those arrows in carefully. And the ramp itself is going to absorb this component. All right, the component of the gravity force. The gravity force is straight down. And if you think about it as the hypotenuse of a right triangle that's tipped so that it's, in line with the ramp itself. So, in other words, most of the time we do the right triangle with, one side parallel to the ground and one side straight up vertical. But if you tilt the right triangle here so that one side is parallel to the ramp, then that black arrow there, that's the component of the force. Try to sketch that in. Make a right triangle. That black arrow there is a component of the force into the ramp. Now, if the ramp is not made out of Jell-O or water or something like, that doesn't have any pushback, if it's a nice rigid ramp, then it's going to balance that black arrow from gravity. But there's nothing pushing back along the ramp. So if this is all that's acting, you're going to get some sliding down the ramp. It's going to accelerate downward. And this is a fairly steep one. If you were in a car driving straight down this hill, you would be going, oh my goodness, this is too scary. If you were on skis on a mountain, and a mountain is this thing out, in other states of the Union, this big pile of rocks. Frequently there's a lot of snow on top, and people put these boards on the end of their feet, and they go sliding down the mountain in the snow. That's called skiing. And if you were skiing on a hill of this steepness, you'd be like, pretty nervous. Unless you were an expert. And, guys, I wouldn't want to ski on that. And I'm a pretty good skier, but that would make me nervous. But, it just depends on the angle. Now, let me take... So that arrow, that black one, gets absorbed by the rigidity of the ramp. Make a note of that. The rigidity of the ramp, you make it out of good stout wood or some kind of metal or something. That rigidity is going to balance the black arrow from the weight force. But now this one here, it's unbalanced. So there's going to be some acceleration down the ramp. Unless you exert the exact same force upward, up the ramp. Now that black arrow, that second arrow that's marked U, that's what you would have to push up the ramp to keep that thing in place. All right? And if you do that, if you exceed that, you'll push it up the ramp. If you do exactly that size force, the two forces, the white one from gravity and the black one from U, they'll balance and everything stays put. All right? And that's the kind of thing that Galileo knew how to figure out, and he understood the geometry of it, and because of that, he was able to defeat Aristotle's idea of motion, that anything in motion must have a force acting on it of some kind, and that if it's at rest, then there's no force acting on it. All right? Another thing that Galileo said was, take for instance this kind of idealized picture of a foot. Are those? I don't even think those guys are. I guess they are wearing a face mask. Yeah, they're wearing a face mask. So, anyways, a quarterback throwing a football to the wide receiver, and the idea that Galileo said, look, if there's no forces horizontal and there are forces vertical, you can separate out those two components of the motion. And that's what these two sets of these sets of arrows represent. The vertical arrow represents the speed or the velocity in the y direction, and the sideways arrow, notice that the sideways arrow never changes in this diagram. And ideally speaking, the horizontal component of the velocity for a baseball or a football or anything you may throw from looping in an arc like that, the horizontal component never changes. And you may say to yourself, Dr. B, why does the horizontal component never change? And the answer to that is, the horizontal component of the motion of the velocity never changes because there is no such thing as vertical gravity. There's no such thing as horizontal gravity. Gravity is only vertical. Make a note of that. Gravity is vertical. There's no such thing as horizontal gravity. So those sideways arrows, the horizontal arrows in this one, they're all the same size, whatever it happens to be. It's only the vertical arrows where there is some gravitational force, there is some acceleration, there is some delta V, and you can see it. The vertical arrows start bigger, get smaller as the football gets to the top of its motion. It disappears at the top of the motion. And then it reappears, but now on the way down, now the vertical arrows are going downward, and the fifth picture, the fifth snapshot of the football, that vertical component is downward, and it's as big downward as the first one was upward. Let me repeat that. The vertical velocity component in the fifth frame is as big downward as the vertical velocity component in the first frame was upward. All right? So if the first frame is 20 meters per second upward, then this fifth frame is negative 20 meters per second, or 20 meters per second downward. All right? Now, there's lots to think about, and as I said, we're going to be talking about this until the proverbial cows come home. But before we go any further, I want to ask you some questions using your iClicker, so go ahead and turn those babies on. And if you haven't used your iClicker yet, what you want to do is follow these instructions. Go ahead and show this. You press and hold the power button for 2 seconds. The letters will flash in the upper left, and you type in D and then D again. You'll get the Go Nitro message, and then and then it'll say ready. Okay. So do that, and everything will be good. All right. Now you should be getting your ready messages. Now here's your question. Kind of an idealized question about a blue car. Read very carefully. The entire room went quiet. Engage brain, disengage mouth. Very good. Adam, got him right where we want him. So think about this and answer very carefully. And this is kind of a question. Do you know what the concept of speed, velocity, acceleration, do you know what those concepts are? That's what this question is about. All right. 20 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, B is the correct answer. Most of you got that correct. Yeah. Constant speed means, so colloquially speaking, constant speed means the speedometer needle is at a certain position and it doesn't move. Constant and to the right means you're just you're not swerving to away from straight to the right. Right? So you're not hitting the steering wheel. You're not turning the steering wheel. Right? So your velocity is constant. All right. Now here's just a little sketch. That you could say, for instance, that the initial velocity vector. And by the way, students, the term vector, if you haven't read it in the textbook, is used to describe any physical quantity that has a spatial direction, or a spatial direction and a length of some kind. So the length of a velocity vector is the speed, whatever the speedometer says. And in your car, you have a speedometer that reads out, so many miles per hour or something like that, but it doesn't really tell you the direction. I mean, your eyes tell you the direction that you're going. They better. But the speedometer doesn't. So the length of a velocity vector is just the speed. And I have a comma here, and then I have a word, right word, to denote the direction. Now, if we were going to be fancy, like in an engineering class or something, we might use degrees and do a little bit of trig and stuff like that. But we're keeping things fairly simple in this class. Right word is fine for this example. Next question. Question number 2. You observe a can of Pepsi on a tabletop, like right up here. It's at rest. Which statement is true of those 4? Go ahead and vote. Wow, this is interesting. Okay, 20 seconds to vote, starting now. Good, I see people pointing at the screen and discussing things. That's what I want. I love to see that. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Go ahead and show them this display, please, Terry. Yeah. The correct answer is B, actually. And most of you voted outside of that. In fact, the majority of you voted for a wrong answer. Go ahead and switch over to laptop, please. Here's the right answer. And go ahead and draw a little diagram. You could write a dot to symbolize the center of mass of the can of Pepsi. But I'm going to keep the can of Pepsi up there. All right, now, here's a force that's acting on it. There's no such thing as horizontal gravity, but for darn sure, there's a force of vertical gravity, and it's always downward. All right, that's this arrow. Now, this tabletop is nice and solid, just like these up here. All right? It's not made of Jell-O. It's not made of water. It's not made of air. It's nice and rigid. And why do we know it's rigid? Because it is described as being at rest. So the rigidity force, can be drawn in this way. So draw an equal size arrow with the tail of it right in the middle of the Pepsi can, or right at your dot, and make it the same length as the weight force arrow. And the weight force arrow is downward. And make this one upward, but the same length. Just kind of eyeball it in. And my arrows actually are the same length in pixels. I think they're, no, they're not 174. They must be 300 pixels tall. But both of them are the same length, all right? And so here's your logic. There's no delta V, it's at rest, so there's no acceleration, all right? No acceleration means there's no unbalanced external force. All right? So make a note to yourself. This object is at rest, but it has forces acting on it. The external force of gravity, that's the gravitational pull from Earth itself, aimed directly downward toward the center of the Earth. And then the other external force, it's not a force that the can exerts, it's the rigidity force of the table. So there's two external forces, but they balance. Now let me make one more comment. This concerns external forces, whether balanced or not. And that is the side Yeah, keep talking, man. If I can't see you talking, then it must not be talking, right? Is that it? I can hear you talking up here, man. Don't do it. You're distracting your neighbors. All right? So the negative or the opposite of external force is internal force. Now, what is an internal force for a can of Pepsi? Well, it's the force that holds the can of Pepsi together. You know, it's made from aluminum sheeting, and the aluminum atoms, you know, they try to stick together. They're bonded. It's a metallic bond, they call it. All right? The electrons in the aluminum, orbiting the aluminum atoms, they interact, and they form bonds. And that's what makes it a good, tough metal. All right? So that's an internal force. All right? So the internal forces that are acting in the can, keeping the atoms together as a can and so forth, those are not going to move it from A to B. But external forces can. So if there was no rigidity force, there would still be the weight force downward, and it would move from A to B. So if you take the table away, that can of Pepsi is going to start accelerating downward. All right, so that would be an unbalanced external force. And that brings us to Newton's second law. All right, if you do have external forces that are unbalanced, you're going to accelerate. And what Newton said is you can measure the acceleration and the mass of an object and the size of the push or the pull that you provide or that your car motor and transmission provide. That determines your acceleration. So make a note, acceleration, we can calculate it based on distance and time measurements. You know, we know how to do distance. We know how to do time. Time, we can use a pendulum if we had to. Would be very precise, but we could use a pendulum. And then distance, all you have to have is a meter stick. But you could pace things off, you know, if you know the length of your step. And so now mass is a different measurement, but it's measurable. And that's what we're heading for here. So what you do is you add up all the forces, and if anything does not balance, then you get a net force. All right? So that's like saying, well, I have a positive bank account, a positive balance of $100, and then I make a debit of $67. So my net balance now after the debit is 100 minus 37, 33. Okay, so you have a net of 33. Question, Katie?
So anything at rest has more than one force acting?
Incorrect. Anything at rest may have zero forces acting on it, or it may have multiple forces, but if it's multiple forces and it's at rest, they balance exactly. So multiple forces but in balance, or zip-zap forces. Okay, so like way out in space, you know, far, far away, something's just kind of sitting there. You know, there's no real forces on it. Or here on Earth, multiple forces, but the upward rigidity force balances the downward weight force, for instance. Okay, so that would be okay too. So two different flavors of being at rest. One with balanced forces and one with zero forces. And for both of those, the net force is zero. But now, this example is considering forces that aren't quite balancing out. All right, so, and we call it the net force. So example, Dwight Howard and LeBron James, let's say that Dwight Howard has 100 units of force to the right, so we'll call that plus 100. And let's say that LeBron James, the notorious wimp that he is, can only provide 80 units of force to the left. So he gets a minus 80. I don't like LeBron James. I would like him if he came to play in Orlando, but I used to like Dwight Howard, but he left Orlando, but still use this example here, so it's pretty good. So anyway, so there's LeBron James, LBJ, minus 80's leftward. So the two arrows here are precisely measured, you know, in the ratio of 80 to 100, you know, so 4 to 5. And so that means that the net force is rightward. There's 100 units of, there's 20 more units of rightward force from Dwight Howard. And so Dwight Howard goes toe-to-toe with LeBron James, and he's still got 20 units to the right on top of that. So, so we would say that the net force is rightward, and we would make a little sketch down here. So these are two separate sketches. One has the two constituent forces, Dwight Howard and LeBron James, and one has the net force, which is the combination of the two constituent forces. Another thing that Sir Isaac Newton said, if you have, so get your net force, if it's positive, you know, to the right, or if it's negative to the left, or, you know, whatever direction it is, if you have more of it, you're going to have more acceleration. You're going to have more delta V over delta T. All right, and we can measure all that. And we can measure delta V. You know, make some time and distance measurements. You know, make a delta V out of it, and then, you know, elapsed time, delta T. We could do that. Have done that. So the more push, the more acceleration. But if your object has more kilograms of mass, then you get less acceleration. So that's like saying if the same person exerts a force on a grocery cart that's loaded with a lot of canned goods, for instance, that's really heavy stuff, then it's not going to accelerate very much. But if the same person then unloads it and just puts one can in there, so it's way lighter, and pushes with the same amount of push, he's going to get more acceleration. All right? So the more mass, the less acceleration. Less mass, more acceleration. Now, the way that works out is that more force, more acceleration, force is in the numerator. More force, less acceleration means mass is in the denominator. And this is the form that Sir Isaac Newton said will do the job. You know, he could have had the square of the mass or the square of the force in the numerator. But he said, no, this is the simplest one, and this is the one that is the way nature thinks. Nature accelerates things in direct proportion to the net force and in inverse proportion to the mass, right? Another way to write that is if you cross multiply, simply this, F net equals MA. And this version here, F net equals MA, that's the conventional formula for Sir Isaac Newton's second law of motion. Now, if you know anybody in the engineering department, and there are people from engineering in this class, I'm not going to look at anybody, but I do know that there's a few. Those guys over there, especially the guys that are really annoying, they think they know everything. You know what they're constantly thinking about? F net equals MA, F equals MA. It's like, and same in the physics department. It's just, you know, think about it a lot. It's because it governs the universe, really. You know, this law of Newton, you know, this is what NASA has to do to figure out where that spacecraft is going to go on its orbit, where it's going to land on reentry, and how long is it going to be there. F net equals ma, or a equals F net over m. What they're trying to do, is figure out, what's the change in the velocity, and get those trapezoids going, and figure those babies out, and then they know where it's going to go. All right. So engineering physicists, we all think about F equals ma. And let's take a look at some more details about it. Now, up at the top right there is an equation, A equals delta V over delta T. Now, that's what I call the definition of acceleration. The acceleration is an increment of velocity over an increment of time, or over an elapsed time. Time interval. And we can measure the time interval, using a pendulum or any kind of a timer. And we can construct or calculate delta V if we get a couple V's, V1 and V2. And how do we get V1 and V2? We measure some distance and some elapsed times. Or we look at the speedometer. But if you're making physical measurements for speeds or velocities, you got to have spatial distance measurements and temporal time, elapsed time measurements. Now, the next two equations, the second and the third, those are just Sir Isaac Newton's second law. Now, here's another version that I really like. F is equal to m times delta V over delta T. Now, that's taking the third equation and erasing the A and putting delta V over delta T in its place. Now, the reason that that's interesting now is because we're a little bit closer to our basic measurements. That equation, m delta V over delta T, delta T is a direct physical measurement. M, the mass, is a direct physical measurement, in a balance scale, for instance. And delta V is a calculation based on direct physical measurements. All right, so here are the measurements that you need. Time, distance, and mass. For all these. Actually, the top one just means time and distance. But the Newton's laws, the last three on the right, require distance and mass as well. So you make those measurements, and if you get good measurements, then you can calculate velocities and delta velocity from that, and acceleration. Right, so you can do those calculations based on measurements. So what we would say is that velocity and acceleration are based on measurements, and but there's no way to measure a force. The only thing that we can measure is an acceleration and a mass. Now, stopping time, delta T, has an effect on the force, and that is most clearly seen in this last version of Newton's second law. Newton's second law, F equals ma, the world over, but this version here on the lower right, F equals m delta V over delta T, that highlights that the elapsed time, or the stopping time, is in the denominator. And if you have a lot of stopping time, that means your denominator of that expression in the lower right is going to be a fairly big number. So your force, your stopping force, is fairly small. By the same token, if you have a shorter or less stopping time, that means your denominator is smaller, and when you put something in the denominator that's fairly small, it means the entire quotient, when you calculate it out, is going to be a lot bigger, right? And so, and that's related to the joke about Chuck, or the fact about Chuck Norris. The math department, if you ask the math department, is it possible to divide by 0? They always say, no, it is not possible to divide by 0 because 0 is too small. It doesn't have any size. But the true answer is, it's impossible to divide by 0 except for Chuck Norris, who's done it twice. Now, examples of stopping force are, for instance, box jumping. If you do plyometric workouts over at the rec center, and we're going to have some homework on this. It won't be homework 4, it'll be homework 3, I think. The idea of box jumping, you want to land and flex your knees. If you land stiff-legged, you're going to hurt your knees. And why are you going to hurt your knees? Because your knees have to absorb a lot of stopping force. Your whole body has to absorb it, but the knees are the ones that are most easily punished. Your bones and stuff can take a lot of punishment, but knee joints and stuff, they don't like to take a lot of force. All right, so as you bend your knees when you land, bending your knees means you come to rest slowly. Here's another example, and you can write this one down. This is example number 2. If you're in a car and you're up north somewhere in the winter, driving on a snowy road, and just for fun, you decide to go into a skid, and your car goes off the road into a snow drift. And a snow drift is, like up north, it's the snow is sometimes so deep that the snow plows plow it off the side of the road and makes these big mounds of snow. And it's really fun to jump into them yourself, or if your car goes out of control and goes into the snowdrift, it's not going to hurt it. All right? And that's because a snowdrift is gradually going to slow the car down. So delta T, stopping time for a snowdrift, is big. Right? So second example, also big stopping time, stopping your car in a snowdrift. Third example, which I hope you never have to experience. Snowdrift is nice, and it's actually kind of fun, especially if you can get out of the snowdrift. But here's the third example, not fun. Your car stops by going into a brick wall. All right? Now, going into a brick wall, a lot of rigidity. The stopping time is very, very short. So, small denominator, big stopping force. Because delta T, so for a brick wall, delta T is very small. All right? So if you have a car traveling at 15 miles an hour and it goes into a snowdrift, it's going to take a good second or so to stop. But if you have the same car going at 15 miles an hour, it's going to take a small fraction of a second to stop. All right, so those are additional examples in addition to this box jumping. Now, I have another clicker question for you, so get your clicker handy. And what we're going to use is to go ahead and make a note to yourself mentally, if not on paper. We're going to use F equals ma. Newton's second law. And here it is. You have a liter bottle of water. All right, so that's 1.000 kilograms. Plus or minus a little bit for the plastic, but we'll just call it a straight 1.00 kilogram. You accelerate it with a pull force, and the acceleration is exactly 1 meter per second squared. Right now, gravity is 9.8 meters per second squared. So this is kind of a gentle acceleration. You could do it. So what is the size of your net force using F equals ma? Go ahead and vote. Dare. Thirty seconds. 10 seconds. 5. No. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, you guys are geniuses. Most of you got it right. It's just mass times acceleration. So that means it's 1.00 for the magnitude. And then the units are kilogram meters per second squared. And you may say to yourself, Dr. B, what on earth is that? Well, my wonderful student, that is the official unit of force in the metric system. It is called the Newton. A force of 1 Newton accelerates 1 kilogram object at the rate 1 meter per second squared. All right, now we're going to do another calculation here. This one's actually going to be a calculation. You're going to type in a number, so hit the refresh key on your calculator. And after you jot this down about the official unit of force in the metrics, you know what the official unit of force in the English system is? The pound. So when you say, well, my weight is so many pounds, that's actually, you're telling them the force. But we still say that instead of kilograms. All right, how about a 342 kilogram T-Rex? Well, let's figure out the weight force of this baby. All right. Now, what's the gravitational acceleration? So we're doing F equals ma, and 342 kilograms is the m. What's the a that we should use for a weight force? 9.8 meters per second. And not 9.81. Don't start coughing, man. All right, here we go. Go ahead and calculate to the nearest whole number, to the nearest Newton of force. So we're doing F equals ma again. And try to round off carefully. All right. No, I don't want a decimal point. I want a whole number. Round off accordingly. Yeah. It says what? Hit the refresh key. Got it? Have you got one? Then up. Okay. Yeah. So whenever we switch from multiple choice over to numeric, we have to hit the refresh key. And you should jot this down too, so you know how to do it. Because a week from today we're taking our, is that right? Mm-hmm. The 7th, our first midterm. So we got to be ready. No napping next Tuesday. Do not let me catch anybody napping. Today it's all right. If I catch you napping, it's all right. But on exam day, no. You must be alert. All right, 30 seconds. And don't forget to hit the send key. You type in your number and then hit the send key, and then you'll get a check mark. All right? So something, 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 send. right? And I see that most of you have dropped the decimal point. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, 3352. I see a few people typed in 3351. Better double check your round off skills. It's actually 3351.6, I believe, for the T-Rex. And it's basically just 342 times 9.8, and that's the weight force. So the weight force is mg. Right? G is, the gravitational acceleration has its own symbol, and it's usually symbolized G, and that'll work good. All right, let's do some more concepts. I want to give you a few more details about mass. Mass is the quantity that measures inertia, or the quantity that carries inertia, and the way to measure it is using a scale. The basic concept is the more mass you have, the harder it is to change your dynamical state, whether it's a state of rest or a state of motion. Leftwards, rightwards, up, down, whatever direction you're going, whatever speed, it's all harder if there's more kilograms. The metric system unit is the kilogram and the gram. And the gram is based on the cubic centimeter of liquid water in Paris at 21.5 Celsius or something like that. And that's the official size and mass of the gram. In other words, it's in terms of liquid water, which is something that we have a lot of on the surface of the earth. So what you do is you balance your object that you're trying to measure in a balance with some countable number of cubic centimeters of water. So for instance, you put like a liter bottle over here in one side, and then whatever object you're trying to measure, like this basketball, you put that over here on the other side. All right? And then when you get your object balanced, now this picture is not balanced. All right? And that tells you that the basketball, the basketball's up here and the gram of water's down here. That means that the kilogram of water has more mass than the basketball. All right? So the mass of the basketball is less than 1,000 grams. All right? So you take away a few cc's of water and remeasure it. And you find out whatever the mass of the object is. All right? So, and so when they do balance, then you count up how many cubic centimeters you got, or how many liters. I mean, if you have something really big like a car, or a space shuttle or something like that, you might just want the number of kilograms. And so then you count up how many liter bottles of water does it take to balance, the car. The car on one side, a bunch of liter bottles of water on the other side. Right? Count them up, that's how many kilograms you got. All right, so this picture right here is 1,000 kilograms, and obviously the basketball, long day. Long day yesterday and long day today. Almost done. So obviously the basketball is a little bit less than 1,000 grams. And that is actually true. If you take an official NBA basketball, it's less than a kilogram. It's still pretty heavy, but... All right. So this is one of my favorite movies, Transformers. Let's keep going. Now we're going to talk about Newton's second law and spatial directionality. Left and right, north and south. east and west, up and down, to the stars, to the earth, you know, all three spatial dimensions. The net force on an object is equal to its mass times acceleration and points in the same direction as the acceleration. So measure your vectors, your velocity vectors, get an acceleration vector, you know, that's going to point in a certain direction. It is a vector quantity. And that tells you the direction of the push. Or you can do it this way. If you want to produce an acceleration in a certain direction, then push in that direction. I mean, it seems kind of simple, but that's the way it works out. So actually, this is, it may seem simple and trivial. Yeah, you push in a certain direction, the acceleration is in the same direction. There are forces that the acceleration, that the force is actually, no matter what you do, is perpendicular to the velocity, the magnetic force. The force on a charged object moving in a magnetic field is always perpendicular to the velocity. It's never in the same direction as the velocity. It's kind of strange. That's the way magnetism is. All right, so if you get a force 45 degrees from your velocity, you get some speed change and some direction change. Why do you get some speed change? Well, if this is your car, all right, and you're getting this little ball marked alpha coming in from aft and port at 45 degrees, it's going to bounce off your car, right? So it's going to give you a little bit of forward oomph and a little bit of starboard, a little bit of rightward oomph. All right? And so a little bit of speed change and a little bit of directional change. All right? And what we're going to do in the homework, which I'll try to get ready for you tonight, and I'll make it fairly small, but a good thoughtful set of homework questions. Did you know that I had some students ask me for more homework over the weekend? Yeah, it's unbelievable. They messaged me, and I'm not looking at anybody. I'll look at Darian because she's not. But yeah, I have some students, Dr. B, are we going to have any homework this weekend, please? And I was thinking, boy, this is such a thrilling moment to see students asking for homework. So F net equals MA. Go ahead and write this version of it down with the little arrows. That simply means that it's really a vector concept, a vector equation. And a lot of times we won't have to worry about it because we're only working left and right. If you're just working left and right or up and down only, then positive and minus is fine. You don't have to put those little arrows. But if you're working in all three dimensions, you know, like guys at NASA, they have to worry about up and down, left and right, forward and back. So they have to do a lot of trig is basically what they've got to do. Anyway, so you'll have a little bit of homework on this tonight. Hopefully, if I don't conk out before supper, which I feel like doing right now. Now, next time we come, we're going to talk about Newton's third law. Oh my goodness, Usain Bolt. Look at that guy. Did you know that his advantage in speed is because he's so tall? The way that he runs. Did you know that everybody that you know that walks or runs, it's actually falling forward? A process of controlled falls. And he's so tall, when he leans forward, his fall takes him further forward than all those other guys. And so we're going to be talking about this concept of third law pairs that you'll be able to read about in the book. So I'll see you on Thursday. Look for some homework tonight. You're dismissed. 105.